Good afternoon, everyone. I am Chanda Devnath, one of the PMRF fellows. So today I am one of the TAs of this Retrosynthesis in Organic Chemistry course instructed by Professor Shamik Nanda from IIT Kharagpur. So here I discuss some questions based on some name reactions and other carbon-carbon bond formation, carbon-carbon double bond formation and other different type of reaction which may help you to solve your assignments as well as to attempt questions for your upcoming examination. So let's start. In my last two classes I have discussed about the enolate formation reactions and aldol condensation. Then in the second class I discussed about some name reactions to form carbon-carbon single bonds. So here I will continue that, where first initially I will discuss some reactions by which you can form a carbon-carbon bond. So while applying retrosynthesis, if you see a molecule and you want to make that molecule form its starting material. So how, if suppose there is a carbon-carbon bond in the molecule, so you want to form that carbon-carbon bond. So what are the possibilities, how you form that bond? So that's why I am discussing about this type of reactions. In your assignments also they have given some questions like this. So let's start. So in the last class I have discussed about the aldol reactions. So there is another type of reaction which is called retroaldol reactions. So if you know retro means, as we know that our focus of this course is retrosynthesis. So retro means going backward. So retroaldol reaction is just reverse of the aldol reactions. So what is aldol reaction? First let's discuss about that. As I think the aldol reaction is a reaction that combines two carbonyl compounds to form a new beta hydroxy carbonyl compound. So in this case, in case of aldol condensation reaction, if there is a carbonyl molecule with a alpha hydrogen, with at least one alpha hydrogen in presence of acid or base, that alpha hydrogen get abstracted, and through enolate formation it attacks to the another molecule of carbonyl and form this type of beta hydroxy carbonyl compound. In the last class I may have discussed about the mechanism. I will share the video where you can go and check. Here I am not discussing the mechanism of the aldol reaction. So aldol reaction is overall reversible, because just to break this type of compound you need a catalytic amount of H plus or OH minus. So this reaction is totally reversible. It can go this way and this way also. So consequently, if an aldol, the product of the aldol reaction, is treated with an acid or base catalyst in the aqueous medium, the reverse reaction occurs, which is known as retroaldol reaction. So if you take your product of the aldol reaction and apply to the same condition in acidic or basic, then you will get your initial starting material. So how this appears? So in aldol reaction, what you get? A beta hydroxy carbonyl compound. So this is a beta hydroxy, this is alpha, and this is a beta. So this is a beta hydroxy carbonyl compound. So this is a product of aldol reaction. Now you are treating this beta hydroxy carbonyl compound with a base. What will happen? This will take up this hydroxy proton and it will be deprotonated. After that, through this rearrangement, we will get our starting material of the aldol reaction. Similarly, in this case also, what will happen? This OH minus will take up this proton. This bond comes here and we get our starting materials of the aldol reaction. So this is called retroaldol reaction. So if you have a compound which seems like the product of the aldol reaction and you treat that with a catalytic amount of H plus or H minus, that will give us our carbonyl compounds. So there is a question which came in GATE 2018. So they have given a substrate and asked the major product formed in the following retroaldol reaction when it treated with pyridine sulfonic acid 50% aqueous in 50% aqueous dioxin. So they have pyridine sulfonic acid, that means they have given acidic medium in aqueous solution. So what will be the product formed in retroaldol reaction? Just give it a try, then we'll solve it together. I'll just give 10 seconds. Just try to memorize what we have done in this case. You have to do the same. You just have to deprotonate your hydroxy. Then through rearrangement, you will break the newly formed carbon-carbon bond and will get your desired two carbonyl compounds. So here you just have to find which one is the beta hydroxy alcohol, which one is the your beta hydroxy group. There are two hydroxy group you have to find, because only the hydroxy group which get involved in that rearrangement, it should be beta hydroxy, otherwise it won't be involved in that kind of retroaldol rearrangement. So there are two hydroxy group, you have to find which one is the beta hydroxy. I gave the hint already, so just try to find the beta hydroxy, then the simple one, simple rearrangement you will perform. Okay, let's start. First, so among these two hydroxy group, this is the carbonyl group, and with respect to this carbonyl, this one is alpha, this one is also alpha, this is beta, this is gamma. So which one is the beta hydroxy group? This one. This one is our beta hydroxy group. So it will involve in our mechanism. So how it will go? In presence of acid, this one will be deprotonated and this bond breaks, followed by. So what we will get? Sorry, this one is. Okay, so this one will be your product. Now you have to draw it according to your options. As you see, this bond has broken. So just erase this for simplicity. this bond has broken. Okay, this one has broken. So now this is the carbonyl group. So let's count the member of this ring. 1 2 3 4 5 6. So this should be a 6-member ring. So this option is already cut because it's contain a 5-member ring. Now among these three, so one carbonyl, there is a double bond. One carbon distance, there is a double bond. So here the double bond is 1 carbon distance, but here the double bond is 2 carbon distance. So this one is also cut. So option will be among these two. 1 carbon distance double bond, 1 carbon distance double, which is above the plane, and the OH is below the plane. This is also below the plane. Now this group, you can see this is already above the plane. This is already above the plane. So this carbonyl group should be, because this is above the plane and it was below the plane, and this carbonyl group is already above the plane, so it should be above the plane. So correct option will be option D. Correct option will be option D, because this is above the plane. You can see this is above the plane. Okay, I think it was simple. Let's go to our next topic of formation of carbon-carbon single bond. So this Simon-Smith reaction. This is an organocellulotropic reaction involving organogic carbenoid compound to form a cyclopropane. It is named after Howard Ingerson Simmons Jr. and Ronald Smith. It uses methylene free radical intermediate that it delivered to both the carbon of a alkene simultaneously. Therefore, configuration of the double bond is preserved and in the product, and the reaction is stereospecific. So what is the difference between stereospecific and stereoselective? When you are getting a specific stereochemistry of a product from a specific stereochemistry of the substrate, that is called stereospecific. Now if from a specific stereochemistry of the substrate you are getting one stereochemistry of the product as a measure, then it is stereoselective. Okay, in case of stereospecific reaction, there is no major minor concept, there is only one product which will form. But in case of stereoselective, there is a major minor concept. One product will be major, another product will be minor. So stereospecific means only single product will be formed. So here because the carbene get incorporated into the carbon-carbon double bond from a single phase, from a specific phase, that's why it's totally stereospecific, because it won't get a time to isomerize. It will just come up from one phase and we will get our stereospecific product. So this is the mechanism. So this is our Simon-Smith reagent, which can be formed by using zinc, copper and CH2I2. And when this Simon-Smith reagent is formed, it gets just attacks it. See, it's coming from a single phase of the double bond, and we get our alkene cyclopropane compound. So this carbene is taking 2 electrons from the double bond and giving back to the another carbon of this double bond. So there is one question which came in GATE 2021. The major product formed in the following reaction. So you have to predict which will be the major product formed in the following reaction. Options are given. Just give it a try, then we will solve it together. So the special thing of this Simon-Smith reagent that this type of, as it contains this type of zinc complex, whenever there is a coordinating group in our substrate, whenever there is a coordinating group, which is electron donating group like oxygen or any heteroatom like oxygen, nitrogen or halogen type of compound, that will coordinate with that zinc, and wherever the stereochemistry of that heteroatom, the compound, that reagent will come up from that phase. If it is there is a coordinating atom, if this will coordinate with our zinc, suppose there is an example like this one. Another is this. So one contains a OH group, another contains a methyl group. So in this case, due to coordination with this oxygen molecule of OH and zinc, wherever this functional group is, this CH2 will appear from that phase only, but in this case, when there is no coordinating atom, but it will give a steric hindrance, whereas it's not giving any chelation, but it's giving a steric hindrance. In that case, the zinc ion will come from the opposite phase of this sterically hindered group, okay. So here you can see there is silicon. Silicon does not have any such kind of coordinating property because it doesn't have any lone pair of electron to coordinate with our vacuum d orbital of the zinc. So that's why what will happen in this case, it will give a steric hindrance. It will just give a steric hindrance to the molecule. That's why the reagent will come up from the just opposite phase of this group. So here you can see both are in the same phase, so these are cut. In this case, it is coming from the opposite phase, but as I said, the product should be stereospecific. Whatever arrangement of the substrate was initially, after the reaction also the substrate will be intact, just there is a formation of cyclopropane ring. So here you can see the methyl group just change its orientation from E to Z. That's why it will not be our product. Which one will be our product? Option A. Where in this case, see, the substrate and product looks totally similar. Just there is a formation of cyclopropane ring, and that should be opposite to the silicon compound because it does not have any coordinating property. Okay, but if there is a OTMS, if there was a oxygen silicon type of thing, this type of group is there, in that case it will give a coordinating property because of this oxygen molecule. Okay, you have to check that if there is any presence of oxygen or nitrogen or any halogen, if it is there, then it will coordinate with our zinc complex and give a stereospecific product according to the functional group controlled stereospecific product. Okay, I will just give it a minute, just try to grab it and note it down. Next, go to the next topic, which is acylation of carbon nucleophile. So how we will acylation means how will you form a carbon, use a carbon nucleophile and you will form a bond with carbon with a carbonyl compound. Acylation means you will just form a carbonyl compound adjacent to that carbon center. That is called acylation. So how will you do that? there is different type of reaction. First one is Claisen condensation. So what is this type of reaction? In case of this type of compound with a alpha hydrogen, if we add base, what will happen? So they have given two molecules of this compound. If you just write it open, so this is our now. What is Claisen condensation reaction? Whenever there is a acidic H, whenever there is a alpha hydrogen, and you know alpha hydrogen adjacent to the carbonyl are acidic, so this is acidic. So in presence of this acidic if you add base, what will happen? It will take up that proton and forms an enolate. And that enolate will react another molecule of and that enolate will react another molecule of this compound. So if you draw the another molecule of this compound, this goes here, it will react the ester center of the another molecule, and this gets removed and we get our desired product. So this is called Claisen condensation reaction. So whenever there is a alpha hydrogen, acidic alpha hydrogen, it will get deprotonated in presence of base, and that will attack the ester center and remove the alkoxy group, forming a acylation of the carbon center. So there is one question. So what will be the product form in this major product form in this reaction? I have given 4 options. Just give it a shot, then we will solve it together. As I have discussed already Claisen condensation, so it will be based on that topic. So just give it a try. You have to find the alpha hydrogen first. So just try to find the most acidic alpha hydrogen, which will be abstracted by the base, and that will react with the ester centers. Now see, this single molecule contains 3 ester centers, so there is possibility of intramolecular reaction. That's why they didn't give any other, and there is a formation of ring also. From that you get an idea there is a intramolecular reaction. So try to find the more acidic hydrogen which will react with another ester center. Okay, just try. Now you can see there are 3 ester group. Now how many alpha hydrogens are there? This is alpha with respect to this carbonyl compound. With respect to this carbonyl compound, this is alpha, and with respect to this one, there is another alpha carbon. Now among these 3 alpha hydrogen, which one is more acidic? Which one is more acidic? Okay, so this alpha hydrogen will be more acidic because this is directly connected to this CO2 group, and also it is connected to a small alkyl group, whereas this carbon is connected to a long long alkyl chain, therefore it has greater plus I effect. So this one is more acidic. So let's try to solve this one. If we just try to draw it in open chain model, so this one is CH2, CH2, CA2, CH, CH3, and there is a ester group. Now there is another ester group. So among these alpha hydrogens, which one is more acidic? Obviously this one. Why? Because all these are connected to 2 carbon-carbon bond, whereas this is connected to 2 hydrogen and 1 carbon bond. So that's why it has less plus I effect. It has less plus I, whereas this carbon has plus I effect of 2 carbon bond. So 2 carbon bond. So that's why this one is more acidic. So that's why this proton will be abstracted, and after the abstraction of the proton, what will we get? And if we just draw the after abstraction of the proton, there will be a negative center, and that will attack here. That will abstract this proton, and there will be generation of the negative charge, and that negative charge will attack this carbonyl compound, and OAT will be removed. So what will be our desired product? So our desired product will be this one. See, there is CH3 CO2, and there will be, after forming this bond, there will be another CO2 group. After form, sorry. There will be another CO2 group here. Okay, so the correct option will be option B. I hope it's clear. Let's go to our next topic, to form carbon-carbon single bond. So we all know about the Grignard reactions. So Grignard reaction is an organometallic chemical reaction in which, according to the classical definition, carbon, alkyl, allyl, vinyl and aryl magnesium halides are added to a carbonyl group of either an aldehyde or ketone under anhydrous condition, and this reaction is called carbon. This reaction is very important in case of formation of carbon-carbon single bonds. So this type of Grignard reaction can react with multiple types of compound. Here I have given a short view. If it reacts with the aldehyde, what will form? It will form an alcohol. If it reacts with the ketone, it will also form an alcohol. If it is react with the ester, it will form a ketone. After that, if you add another molecule of RMGX, it will form an alcohol. If you react with any heteroatom or amide type of thing, it will form a aldehyde. After that, so this type of reaction takes place in case of Grignard reactions. So here I have given one example. So they have asked what will be the major product formed in this following reaction. So you have know that Grignard can react with various type of compounds. Here I have shown aldehyde, ketone, ester, amide, a special kind of amide, carbon dioxide, and alpha beta unsaturated ketone. So what will happen in this case? Just try. There are two, you form the, this is called epoxide, this is called epoxide. So from epoxide has, that 3-member rings are highly strained. 3-member rings are highly strained, whereas there is an oxygen atom. So it is highly strained and prone to open. So there are two possibilities. One is bond can open from this position, another is this position. So from where it will open? Just think. So what will form? So in this case, this ETMGBr will attack the less crowded center because it has a alkyl group, so there is a steric hindrance, whereas this does not have any alkyl group, is less sterically hindered, so it will attack to the less crowded carbon center. So what will happen? This will attack to the less crowded carbonyl center. So it will open up. So what will be the product? So the product will be option C. Okay. Let's go to our next topic for formation of carbon-carbon double bond, that is McMurray reaction. So what is McMurray reaction? Two ketone or aldehyde groups are coupled in this reaction to form an alkene using titanium chloride compound such as titanium chloride and a reducing agent. So this reaction is named over its discoverer John E. McMurray. So what is happening here? If you add this carbonyl compound and a reducing agent, it will form this type of carbon-carbon double bond. So how this reaction goes? A titanium chloride, this form a radical. By this it will break. Then undergoes a radical coupling, forming this type of then through a reducing agent it will form this alcohol, and on heating it will give this alkene product. So this is the mechanism where titanium tetrachloride in presence of zinc form this titanium Cl2 and zinc Cl2. Then this single radical will give to the oxygen, and this carbon-carbon double bond will break partially, forming this carbon radical. After that, the titanium has another single electron which will do the same with another molecule of carbonyl compound, and both of these carbon-carbon radical will couple to form a carbon-carbon double bond, carbon-carbon single bond, and after and through a rearrangement it will form this type of alkene as a product. So this is called McMurray olefination reaction, where by using from a carbonyl compound you can couple two carbonyl compound to get a alkene as your product. Okay, I think mechanism is clear. Just give it a So there is a question came in GATE 2023. So what is the major product formed in the given reaction? So the 4 options are given. Just give it a try. As you can see, the reaction going through a chelation type of intermediate or transition state. So this, see, the titanium is attached from a specific side or the same side of this 2 carbon center. So from there you get a hint that how the arrangement of the oxygen will be there. So what will happen here? First, so this titanium will give 1 electron to this oxygen and another to this oxygen. Okay. After this carbon-carbon radical will couple with each other, forming a carbon-carbon bond. and by addition and through protonation we'll get this as our product. So the correct option will be option A. Correct option will be option A. Okay. So this was the McMurray reaction. I hope you guys have understood. Let's go to the another type of olefination reaction. It's called olefin metathesis. Ring closing or ring opening metathesis. So for this one we use different type of catalyst, shock and Grabs catalyst. So this is first generation catalyst, is second generation and third generation. Different type of using this type of catalyst we can cleave a carbon-carbon double bond or form a carbon-carbon double bond from two alkene. So how it goes, if you are given two different alkene and you are adding this Grabs reagent, what will happen? It undergoes a cyclization, like this type of cyclization. After that it will undergoes a metathesis, forming this metallocene and followed by coupling with another alkene, it will form this alkene compound. Okay, so by this using this Grabs catalyst we can couple two alkene to form a single alkene. So if you have two different alkene and from that two different alkene you want to get a single alkene, you can perform this olefin metathesis reaction. So suppose you are performing a retrosynthesis and you have given a alkene. Now you want to break that alkene center and get to another alkene. So how you can do that? So you can do that by using olefin metathesis. So as one question came in GATE 2023. So the organometallic catalyst for the following transformation is, so they have given two alkene and just by using one catalyst they are getting a single alkene. So how it will go, what catalyst they should use? Obviously this one, because as we have discussed right now, Grabs catalysts are capable of doing this. This is Wilkinson catalyst, which is used for hydrogenation reaction. This is used for carbonyl incorporation reaction, and this is also a different type of reaction. But for this type of reaction, the only reagent which will work is this ruthenium catalyst, that is the Grabs catalyst. So the correct option will be option A. Okay. There is another type of olefin reaction which is called sulfonium, stabilized sulfonium. We know about ylide in case of Wittig reaction. Today I haven't added the Wittig reaction in this slide. In the next class we will discuss about Wittig reaction. So here I am discussing about the different type of ylide which is called stabilized sulfonium ylide. So what is called stabilized sulfonium ylide? So we have in the initial of this class we were discussing about cyclopropane ring formation reaction. So how we would get that? By using a Simon-Smith reagent. We can form a cyclopropene ring from a alkene. So there is another type of reagent we form by which we can get a cyclopropene ring. So this is called stabilized sulfonium ylide. If we add this sulfonium ylide to a conjugated alkene, we will get cyclopropene. But if we add this sulfonium ylide to a carbonyl compound, we will ended up getting a epoxide. Okay, but if we add a normal sulfonium ylide to a alpha beta unsaturated ketone, we will get a epoxide. But if we add this type of stabilized sulfonium ylide to a alpha beta unsaturated compound, it will give a cyclopropene ring. Okay, so see the difference. Just changing the stability of the sulfonium ylide, we can change the selectivity of the reaction. Whenever there is a stabilized, it will react to the alpha beta unsaturated double bond, and if it is not stabilized, it will react with the carbonyl compound. So here's one example. Here you can see this is sulfonium ylide, but this is sulfoxonium ylide. So sulfoxonium ylide behaves similar to the stabilized sulfonium ylide. So sulfoxonium ylide ylide are equivalent to this stabilized sulfur ylide. Sulfoxonium ylide are equivalent to this stabilized sulfur ylide. So whatever we get from a stabilized sulfur or sulfonium ylide, we'll get the same product from the sulfoxonium ylide, and from the non-stabilized or normal sulfonium ylide we'll get a different kind of product. So here with one substrate is given, and there are two type of double bond, and there is a one carbonyl compound. So what will happen when we add sulfonium ylide and sulfoxonium ylide? Just give it a try, then we will solve it together. Sorry, 1 second. So ylides are whenever there is a two different charge just side by side, they are called ylide. So here you can see in this case the positive charge and negative charge are just side by side, and that can be delocated into the backend d orbital of the sulfur. So this type of compounds are called ylide. There is another type of ylide called phosphorus ylide, which is like PPH3 plus and CH2 minus. Here also two charges are side by side. This is also a ylide. This is called phosphorus ylide, which is used in case of Wittig reaction. This will I discussed in the next class because I didn't add questions from that. But if you add, I'm just give you an idea. If you add this type of halide to a carbonyl compound, simple carbonyl compound, what will happen? This negative center will attack here. This open up. Forming this O minus. PPC plus is still there. Now phosphorus has a vacant d orbital, so it will attack here, give its electron to this, then it will form a cyclobutane on butane type of ring. Then two ring cleavage, like this one comes here and this one comes here. You get this alkene product. So by using phosphorus halide also we can get this type of compound. This is called Wittig reaction. This is called Wittig reaction. So similar type of case happen in this case of sulfur halide also, but in this case of sulfur halide we do not get any alkene, whereas we instead of that we get cyclopropane and cyclopropane and epoxide rings. In case of phosphorus halide we get a double bond, whereas in case of sulfur halide we get cyclopropane or epoxide ring. So this one also reacts in a similar type of way. This carbonyl, this one comes attacks here, this open up and goes. Okay, so let's go to the next. This is called halide. So whenever there is the mechanism of this sulfonium and sulfoxonium halides are quite complicated. So for this today's class I am not discussing that. I am just discussing the product. In the next I will discuss about the mechanism, because for that I need some structures, because if I want to draw it through a paint it will be quite messy. So whenever I have already told that sulfoxonium halide just behaves similar to the stable sulfonium halide, and I have said that stable sulfonium halide always react with the alpha beta unsaturated double bond, whereas sulfonium halide react with the carbonyl compound. So what will be the product in this case? There will be a formation of epoxide whereas in this case there will be a formation of cyclopropene. Now there is a 2 double bond, but always choose the alpha beta unsaturated double bond. In case of sulfoxonium halide, normal double bond will not react with sulfoxonium halide. Now if you add to the same compound, if you add Simon-Smith reagent, which I was discussing in the initial of this class, like CH2Zn I2. If we add the Simon-Smith reagent, what will happen? So in case of Simon-Smith reagent, it will always react with the unconjugated double bond. It will always react with the unconjugated double bond, not with the alpha beta unsaturated double bond. So in this case, what will happen? It will form a cyclopropane ring with the unconjugated double bond. So from here you can see, just by using different reagent we can get reactivity of the different functional group. Just by adding sulfonium halide we can form epoxide from this carbonyl center. Then by using a sulfoxonium halide we can form a cyclopropane of this alpha beta unsaturated double bond, and again by using a Simon-Smith reagent, we can form a cyclopropane ring of the unconjugated double bond. So let's try this one. So it came in GATE 2018. They have asked that what is the major product formed in the following reaction sequence. So they have given this. So this is sulfonium or sulfoxonium. Obviously this is a sulfoniumylide. So they have given the sulfoniumylide with the base. So what will be the desired product in major product form in this reaction? Just give it a try, then we will solve it together. The major product formed in the following reaction sequence. What will be the major product? So let's try. So this base will deprotonate this center, forming this anion. After this anion, so we know this type anion will attack to this beta position. So this one undergoes a cyclopropionation of this carbon-carbon double bond. So it will come here. The correct option will be option A. Okay. So there is another question. So they have given this dialkene product, dialkene substrate, and they have added Graf's catalyst. They have added Graf's catalyst into this. So we know what happened when we add Graf's catalyst. On using Graf's catalyst, this 2-alkene will just cyclize. Forming this alkene. After that, when we add H2PD and lithium aluminum hydrate, what we will get? This H2PD will reduce this double bond. Whereas lithium aluminum hydride will reduce this amide and form amine. So we'll get, so this will be our A and this one will be our B. Okay. In the next class, we'll discuss about some more reactions for forming carbon-carbon double bond, and also we'll start discussing about different type of oxidizing and reducing agent. After that, we will discuss some retrosynthesis of some big natural products, which will give a clear idea how to apply these small reactions to form a big molecular structure. Okay. Thank you. I hope it will help you.